So welcome again. In this video I'm going to talk about the practical aspects of a Peltier element, and also I will discuss the Peltier effect. So as I showed in the theoretical video, I explained that basically there are two effects. If you have a temperature gradient, then you can produce current which can be measured, or basically you measure the voltage. So that's how this guy works here. So basically this is a thermometer with a K-type thermocouple. And thermocouple is basically just two metals joined together. Both metals are some sort of nickel alloys. It's called chromal-aluminal alloy. So the chromal part contains like 90% of nickel and 10% of chromium, and the aluminum part contains 95% of nickel, 2% of manganese and 2% aluminium, and 1% silicon. And then you join these two wires together. Here it's actually like spot welded together, and then you can measure the temperature. And if you see that I touch it, and then you see the change. And then you can reverse this effect, and that's where you use this guy here. This is the Peltier element. So you connect it to a power supply by these two wires, and then I don't know if it's visible, but you will have a hot side and you will have a cold side here. So this is a TEC 12715 type Peltier element. Basically it can run on 12 volts and 15 amperes, so it's quite high performance stuff. So what you see here is these two sides, and the white ones are made of ceramic Al2O3. So these are basically just to protect the inside and keep everything together, so to keep the structure as it should be. And basically what you have here is you have these two ceramics, and between them, where now it's sealed by silicon or something like that, you have the semiconductors, which are like bismuth based. So I can show you that this can work as well as a thermocouple, because you have two different metals or semiconductors joined together. So I connect a multimeter to this guy, and I will show you that I will change the temperature of the hot side, which is this without the text, and there will be a change in the voltage. So you can see wires are connected, and this is our Peltier here. So as you can see, I touched it and it's already changing. But now I try to put it here. So this is like a metal surface. So that's the cold part, but basically it's room temperature. But now I touch the top part, and you see that there is a change in the voltage. And then I release it, and the two sides will have the same temperature, so the voltage will drop down to 0. And then I can use a more extreme way, so I can have more stronger effect. So I will use a heat gun and blow hot air on the hot side, so I will show you how much voltage you can get, and this will be a bit noisy. So you saw that we almost reached like 500 millivolts, so half volts. But this device is very inefficient to produce electricity by this method. So if you are planning to build a power plant based on this effect, then I have to make you sad that it won't work. But if you reverse this effect, then it can work very nicely. And also, if you make stuff like thermometers from metals, then that would be, or that will be, more useful. So now I will talk about some practical issues regarding the Peltier cooling. So we have our device here. This is actually 4 by 4 centimeters, and the thickness is whatever, I haven't measured it. But so we can start. Usually people are keeping the hot part or hot side cool or at a constant temperature, and they try to use it as a cooler. So either they put it on some electrical chips or circuits or whatever, and they try to cool it, or they can also, or you can use it as a refrigerator unit, but it's not so efficient. So as I said in the previous video, there are like 5 effects fighting with each other, or basically it's a 1 versus 4. So let me do like this. So you have a current running through this block, and then you produce heat basically. So you cool down this side and heat up this side by the Peltier effect, and then because of the current you also heat it up. So that's another effect, and you have the other effect from the environment as well. So if you don't use proper insulation around this block, then the heat from the environment will like warm up the cold side. So you don't want that. And also you have a warm side here, and you have a cold side here. So of course the heat will try to, or not try, it will actually do it. So the heat will flow from the hot side towards the cold side, and will warm this up. So you have to be careful. So first of all, most of the people are using some sort of heat sinks like this or these, or they use a sort of CPU cooler to cool it down. So those are, let's call it air-based cooling systems, and those are not so bad. You can use it for demonstration purposes, but the problem is that you can't really keep your temperature close to the room temperature. So that's not always the best thing. So basically you have the hot side, and then you attach your cooler. Of course you will need a bigger one, and then you will try to cool down this part, and then you will attach something to this part, like let's say a glass of water or whatever, and you will cool it down. But this is not so efficient, because you cannot really cool efficiently with air in this case. So what you can also do is you can have a block like this. So it's a water cooling block. So you attach your element on this block using some thermal grease or something like that to make a good heat conduction between the two surfaces. And then you attach a pump and some water tank and also a radiator to dissipate the heat. And you keep the hot side on a cold temperature, and also due to the heat capacity of the water you can have a more stable temperature while you are running this guy. And it's very important because these devices have like limited capacity to produce temperature difference between the two sides. So usually these devices can produce temperature difference between the two sides around, let's say, 50 to 60 degrees Celsius. So let's say if you can keep your hot side at 30 degrees, then you can achieve minus 30 degrees on the cold side if everything goes well. But of course, you have to use high current to achieve that temperature, that low temperature. So therefore you will have to keep your hot side cool, so you don't have the negative effect from the Joule heating, and also you don't have heat flowing in this direction towards the cold side. And you also have to surround this with some stuff like styrofoam or something in order to keep it cool. And yeah, it's more efficient like that. And so the first problem is when people are trying to use this is the insufficient cooling. So I suggest you either use some very big CPU cooler or you use water cooling. And water cooling is better because you are using a lot of water, so you have a lot of heat capacity. So even if you are not using a radiator, so you're just circulating the water in a closed loop without dissipating the heat, the temperature of the water will raise slowly. And actually I will demonstrate this to you later. So the other problem is that people are using this kind of power supply unit, which is good because these are like small, compact and high performance power supplies. If you can see, this is basically 12 volts and 30 amperes, so it produces a lot of power. But the problem is that if you just simply plug and chug, so you just directly connect it to the outputs, then the thermoelectric cooling element will get all the current which can get. So it will run on 15 amperes or whatever current, whatever is the nominal performance of these units. So, and then that's a big problem because actually for these devices there is a minimum temperature, so what you can achieve as a function of current. So you cannot actually increase the current of these to 15 amperes because you will hit the top earlier. So let's say you can go to, I'm just saying some random numbers, you can go until 10 amperes with some cooling, and then after 10 amperes, if you increase the value of the current further, for example 11 amperes, then the Joule heating will take over, and actually the temperature will not decrease but increase. So you will start to heat up your system because of the Joule heating term. So that will take over. And you can measure this actually. So you just take measurements like increasing the current by 1 amperes or half amperes, and let the device reach its equilibrium. And then you just simply measure the temperature on the cold side, measure the current, and you see what was the equilibrium temperature and the current. And you increase, and you will see that after time there will be a minimum, and after reaching the minimum and further increasing the current, you will see that the temperature will increase instead of decreasing. So the first problem, or no, sorry, the second problem, because the first problem was the cooling. The second problem is that most of the people are using unregulated power supply. So instead of this, I suggest you to regulate the power supply or connect several items or several stuff which acts as a resistance, which can dissipate the heat or just use the current in order to decrease the current which is flowing through these devices. So it's also important to have proper current running through your device. So now I will show you my small equipment and show you some cooling. So probably I will reach some very low temperatures, hopefully. But in that part I will use a different device. So not this one, but the one with 6 amperes. So 12606 or something like that. No, 12706. So let's jump to that part. So this is the setup. So where should I start? So you see this huge bottle here. So this is basically the tank for the water cooling. Water comes, or the water goes through this tube, ends up here, and then the water is being sucked up by this tube here, and then it goes into the cooling block, which cools down the thermoelectric element, and then it goes there, passes through the pump and goes back. So this is a closed cycle, there is no radiator. So at the end the temperature will rise in the bottle, but for the demonstration it's totally fine. And then this back box, it contains 2 thermocouples, or I have connected 2 thermocouples to it. So this is my thermometer, and then you can see that these are like thermocouples. So I'm using this Peltier effect or thermoelectric effect twice. So one is for the cooling and the other is for the temperature measurement. So this is the other, and then I have a 12 volts power supply connected to the pump, and then I have a regulated power supply. I will start with 0.5 ampere, and then I will gradually increase the temperature and wait for a few minutes maybe to have some equilibrium and see that what is the temperature at each stages. And I will show you the thermometer and the thermoelectric cooler from a closer view right now. So I have the other thermocouple attached to the surface of the cold side, and you can see that this wall thing, including the Peltier element and the water cooling block, is embedded in a styrofoam block. So the only way where this loses heat is most probably or mostly the surface of the cooling element. And then you can watch the temperature here. The temp 1 is the temperature of the water, and the temp 2 is the temperature here on the cold side. So as you can see, this is the room temperature now. Well, it's summer, so it's a bit hot. But now I will start everything, and I will start to explain everything as well. And one more thing is that the thermocouple is attached to the surface of the cooler by a drop of water. So it's not the best thing, but I try to make something. So I start the pump first of all. So now the pump is running. You can hear the noise. So I can see that the water is circulating properly. So now I turn on the power supply, and first 14 volts is the voltage which I use, and 0.5 amperes. I will write it somewhere here on the screen always. But let's turn it on now. So as you can see, the temperature already started to decrease. So now we are at 19 degrees within like 10 seconds. So it goes down quite rapidly. Or goes down in the beginning rapidly, and then it will be slower and slower. But the voltage is now just 1.86 volts. So of course, because I'm not running the device on the maximum current. But yeah, since I've been talking, the temperature decreased like 10 degrees or more than 10 degrees, so within like 1 minute. And the water is still more or less stable, so it's like 28 degrees Celsius. And as I said, there is no heat dissipation. There is no radiator or something else which can dissipate the heat. And now we reached some sort of equilibrium. If you see that the temperature got stuck at like 15 degrees, so I increase the current to 1 ampere. So now we are at 1 ampere, and 3.45 volts is the voltage. And now you see that the temperature dropped rapidly. So now we wait a little bit. So you can see that the temperature of the water is still stable, because as I said, it has a large heat capacity. Actually, I should have started this with fresh tap water, so at least I could get some lower temperatures in the beginning for the water. And now you see that the, let's call it equilibrium temperature, is around 5.8 volts degrees Celsius, sorry. So now we can go down and increase the current to 1.5 amperes. So now we are at 1.5 amperes and 5.1 volts, and we reached negative temperatures. So the maximum current of this device is like 6 amperes, and already at 25% we are able to go below 0 degrees. And now I assume that the water droplet is already frozen on the surface of the thermoelectric cooler, so that's quite nice. And you see that the water temperature is still okay, so we did not go up too rapidly with the water. But on the other hand, the Peltier element cools very nicely. So we reached like minus 1.7, and we can go further. So I increased the current to 2 amperes. So 2 amperes and 6.6 volts, and the temperature of the cold side of the cooling element is like minus 7.5-ish. Water temperature is still stable, more or less. It went up like 0.5 degrees, but on the other hand, we already cooled the thermoelectric element by 30 degrees. So, I mean, if we still consider that the room temperature is the temperature of the water, which is more or less true, then we are like 30 degrees away from that, roughly. So now I will make a larger jump, and I want to go down more in temperature. So now I will increase the current to 3 amperes. So we are at 3 amperes, 9.43 volts, and we are at minus 16 degrees Celsius. So we are almost 40 degrees away from the room temperature. And still we are not experiencing any problems because of the current. So the current is still okay, so we don't have negative effect from the Joule heating, or the water cooling is so efficient that we don't face that problem yet. So now I go and increase it to 3.5 amperes. So 3.5 amperes, 10.83 volts. We are at minus 18.7 degrees Celsius. And everything is still working. Actually, since the room temperature is quite high, we are losing a lot of heat through this surface. I can feel that it's a bit cold here. So I think we can improve or increase the measured temperature there by just putting some kind of insulation material on top of it, like a sheet of paper or something, just to keep the air there. So I will increase the current to 4 amperes now. So 4 amperes, 12.26 volts. And now the water, the temperature of the water has increased by almost 2 degrees Celsius, and the temperature on the cold side is below minus 20. So it's quite cold there. So now let's jump to 4.5. So 4.5 amperes, 13.73 volts, minus 21.6 degrees Celsius on the cold side. And if you have noticed, then the temperature is not decreasing as it was decreasing in the beginning, despite the steps. So there you can see that the Joule heating is more and more stronger. So actually around this current, maybe if I increase the current a little bit more, then there will be a heating effect. So I will try to go up to 5 amperes and see what happens. So I tried, but we hit the top of the Peltier device. So at this moment I can only go up to 4.6 amperes. And we reached 14 volts, and I don't want to go higher above because I don't want to mess up everything. So now I show you one more cool thing. So I will measure the voltage after I switch off the power supply and show you the reverse effect of this. So now we have a cold side and a hot side, so therefore there is a voltage produced. So I will show you that voltage is, we can measure that voltage, and this voltage will decrease as the cold side goes down to room temperature. So you can see the voltage there, and now I'm going to turn off the power supply right now. And you see that there was like 2 volts in the beginning, and now it's decreasing and decreasing. Now 0.7 volts, 0.6, and the temperature on the cold side is rising. Now we have like 0.25 volts. 0.1 almost, and you will see that the voltage will be 0 if the two sides are at the same temperature, because there won't be any temperature gradient, therefore there won't be any voltage produced. And you can see from the speed of the heating that actually there is a huge heat flux between the two sides of the thermoelectric element. So it's very important to keep your hot side cool enough so you have the less possible heat leakage towards the cold side. So that's very important. And now you see that the temperatures are almost equivalent with each other. So there is like 1 degree Celsius difference, almost. So then we have like 20 millivolts. And now, due to the cooling, the slow cooling, so now the two temperatures are almost the same. It will take a lot of time to get the same temperature, I guess. So you can see that barely anything is produced now, because the temperature difference is basically nothing. And now the temperature difference is maybe produced because the water is actually a bit more warm than the room temperature itself. So if I just turn off the pumping and let the water which is here reach the room temperature, then there won't be any voltage produced. So just to summarize my thought, you need a decent cooling to be able to go down to very low temperatures, and I suggest you to use water cooling because it's a bit more messy because of the liquid, but more silent and more efficient because of the heat capacity of the water. You should use some insulating material like I used, so you should use some styrofoam. You should use very good connection between the block and the heat cooling element. So when you attach the cooling block to your cooling element, then you should use some very good thermal grease or paste. Just make sure that you have even surface and you spread the thermal grease evenly and there is good contact. You can also use some clamp or something just to push the Peltier element against the cooling block. So, but if you use something to clamp together the cooling element with the cooling block, then you should make sure that that is not a good heat conductive material, because otherwise you will lose a lot of cooling due to the heat transport through the device which you use to clamp. So that's another good advice. And another is that you should use regulated power supply, and you should measure where is the maximum current, because if you run your device on the maximum allowed current, I am pretty much sure that you are not able to reach the lowest temperature which can be reached with your setup. So make sure that you are able to regulate the power supply, and make sure that you can find the minimum temperature by choosing the maximum current which is still like usable. So I think that was all. So if you have any questions or want me to do more experiments with this device, just let me know and I will try to fulfill your requests. So see you next time.